Welcome back, everyone, to today's Explainer. We're officially talking about the end of lugging around heavy metal air tanks like some kind of 20th century pack mule. Seriously. Today we're diving into something straight out of a high-tech cyberpunk novel, a fully autonomous cybernetic breathing loop. It's essentially the birth of a system that dynamically breathes with you. So we're going to unpack the absolutely cutting-edge science of graphene functionalization for autonomous rebreather architectures.
I mean, think about it. What if you could just breathe underwater forever, right? It sounds like pure science fiction, but as we'll see in the source paper we're exploring today, this is actually a real, tangible engineering hurdle being solved right now. And it's not magic, it's being done by leveraging incredibly precise nanoscale physical chemistry.
Okay, let's dive straight into this. Think of this as our system boot sequence. First, we'll hit the deep dive bottleneck. Second, the pristine graphene solution. Third, generating O2 and scrubbing CO2. Fourth, the hydrogen power loop. And finally, the cybernetic brain on the edge.
All right, booting up Section 1, the deep dive bottleneck and our current CCR limitations.
So, to understand why this new architecture is such a massive game changer, we kind of have to face the severe physical limitations of our current underwater gear. Traditionally, closed-circuit rebreathers, CCRs, they rely on calcium hydroxide, basically soda lime, to scrub carbon dioxide, and it's an archaic, strictly consumable one-way chemical reaction. You're stuck carrying bulky, high-pressure oxygen cylinders and these finite chemical scrubbers. The second they run out, your dive is over, done. But the future? It relies on autonomous architectures based entirely on nanoscale physical chemistry. We're talking a monumental shift to high surface area regenerable absorption for CO2 and direct photocatalytic splitting of water to actually generate oxygen. It's literally the leap from a heavy, finite tank to this incredibly elegant, self-sustaining system.
Moving on to Section 2, the pristine graphene solution and its nanoscale architecture. I gotta tell you, I am genuinely amazed at the material engineering required to make this leap from consumable to self-sustaining actually function in the real world. Now, the absolute magic number for this entire architecture is 1 to 3. We must use exactly 1 to 3 layers of pristine graphene. And why pristine? Well, because while standard graphene oxide is super easy to work with, covalent oxidation completely wrecks its structural basal plane, which totally ruins electron mobility. Pristine graphene, on the other hand, gives us a near-perfect sp2 carbon lattice, which ensures ballistic electron transport. It is insanely conductive. But yeah, there's a major catch. It's chemically inert and highly susceptible to van der Waals agglomeration. Basically, that just means the sheets desperately want to irreversibly clump together.
Now, what's really interesting about this next part is how they solve that clumping problem without destroying the graphene's perfect lattice. Engineers deploy this brilliant two-phase hierarchical functionalization. Step 1 is primary non-covalent pi-pi anchoring. So instead of violently oxidizing the graphene, they use highly aromatic purine derivatives as molecular bridges that thermodynamically stack right onto the graphene plane. Then step 2 is secondary steric polymer shielding. To keep these new chemical nodes from being physically blocked if the layers do try to restack, they encapsulate them in specific polymers. We're talking like a highly porous PVA aerogel for the gas scrubber or a Nafion fluid matrix for the liquid catalyst. This basically keeps the graphene chemically active but physically separated.
For those of you who absolutely love the physical chemistry behind this, here's the governing thermodynamic equation for that anchoring process. Delta G bind equals delta H VDW minus T times delta S. In simple terms, this shows how the system perfectly balances those van der Waals attractive forces with entropic penalties. You know, think of managing those penalties like trying to pack a tightly organized suitcase. You're making sure everything fits perfectly without descending into total chaos. It allows those pyrene molecular bridges to stick to the graphene like nodes on a digital grid, without ever altering the delicate carbon lattice itself. It's just brilliant.
All right, let's hit Section 3. Generating O2 and scrubbing CO2, the gas exchange core.
With our material structure locked in, we enter the actual life support core of the system. Let's look at the chemical journey of gas exchange. Think of this oxygen generation module like an ultra-efficient artificial leaf. The primary photocatalyst here is graphitic carbon nitride, and it's driven by an internal UV LED array to literally split ambient water into oxygen. But here's the thing. Normally, this material fails super quickly because the electrons and holes recombine way too fast. But here is the genius application of our material. The pristine graphene steps in as a high-speed electron sink. It catches those fast-moving electrons instantly, driving the recombination rate effectively to zero.
This ensures a steady, mathematically sound flow of fresh oxygen, pulled right from the water around the diver.
But at the same time, we've got to deal with the carbon dioxide being exhaled, right? The scrubber relies on what's called a Zwitter ion mechanism. So our pristine graphene is coated in amine groups that reversibly capture CO2 molecules under dynamic pressure. But this adsorption process is highly exothermic, meaning it generates a massive amount of heat. However, because pristine graphene is an incredible thermal conductor, it shunts this extreme heat straight from the core of the aerogel all the way out to the external casing of the rebreather. It literally uses the cold, infinite heat sink of the surrounding ocean to cool down the fiery reaction of your own breath. I mean, it is a stunningly elegant piece of thermal management.
Let's move on and see how this builds in Section 4, the hydrogen power loop and thermodynamic recapture.
Because when you split water, you don't just get oxygen. You get a very dangerous byproduct. The stoichiometric reality of water splitting is that you produce a high volume of diatomic hydrogen. So now we have highly flammable hydrogen gas inside the diver's breathing loop. That is a catastrophic flammability risk. And we can't just vent it outside because bubbles create unacceptable acoustic signatures. So to solve this, the architecture places a highly specialized palladium alloy membrane right next to the reaction chamber. This palladium selectively absorbs that dangerous hydrogen, allowing protons to safely diffuse right through it, all while completely blocking the oxygen and the water.
Look at this like a clean terminal readout of the system's engine schematic. To circumvent a zero-sum thermodynamic loop, that captured hydrogen is routed directly into the anode of an integrated micro-PEM fuel cell. On the internal side, the hydrogen is broken down into protons and electrons. Then, on the external cathode side, superhydrophobic aligned carbon nanotubes extract trace-dissolved oxygen directly from the seawater. The overall cell reaction combines that hydrogen and seawater oxygen to create water and, this is the best part, delta E, electrical energy. The system literally flips a hazardous byproduct into a supplemental power supply to run those heavy-draw UV LED lights. No waste.
Bringing all this physical chemistry together, Section 5, Cybernetic Brain on Edge, Edge AI Regulation.
Listen, you absolutely cannot manage this dynamic, volatile web of physical chemistry with passive mechanical valves. You need a hyper-efficient, sci-fi noir digital brain to govern the whole shebang. Enter the FGSGR framework, which stands for Frequency-Governed Self-Graph Reasoning. It's a neurosymbolic AI architecture. And since an autonomous diver can't rely on an external data tether going all the way to a surface ship, this AI operates entirely locally on edge hardware, specifically an NVIDIA Jetson Orin Nano. It has to make critical, life-saving adjustments, like modulating photon flux and triggering scrubber purges with millisecond-level precision and absolute zero latency.
To pull this off without crushing computational overhead, the AI diagnostic router uses a 5-state metacognitive tracking grid. It is constantly reading the diver's multimodal telemetry. We're talking your respiratory rate, the partial pressure of oxygen, your carbon dioxide output. It instantly condenses all this data, seamlessly mapping a human being's real-time biology directly into the math of the chemical kinetics happening inside the loop.
So the crucial point here is exactly how it applies this data. The framework utilizes active inference, which mathematically minimizes variational free energy. Essentially, it's minimizing prediction errors. The AI continuously calculates the difference between the diver's expected internal physiological state and the incoming sensory observations of the rebreather's efficiency. It doesn't just passively react when things go wrong, it acts predictably to modulate the hardware, squashing chemical and biological errors before they even happen. Just listen to how the source paper summarizes this, because they hit the nail on the head. Quote, by acting on the environment, the FGSGR agent minimizes prediction errors, ensuring a perfectly tailored and chemically stable breathing loop. End quote. This brilliant fusion of zero-latency edge computing and advanced nanomaterials fundamentally guarantees diver safety. The machine intelligence is actively breathing with you, constantly tuning the chemical reactions to perfectly match your metabolic demands.
Which leads us to a pretty profound question. As we seamlessly fuse edge computing AI with nanomaterial chemistry, creating a truly autonomous, self-sustaining life support loop, what limits to human exploration are left to break? I mean, we are officially moving past the days of finite oxygen tanks and entering an era where the deep ocean might become just as mathematically predictable and accessible as the surface. It is just a stunning glimpse into the boundless future of human endurance. Thank you so much for diving into this with me today, and I'll catch you on the next explainer.